Hi everyone, I'm Dr. E. So today we are going to try a few questions, related to the boundary conditions. You can find this question in the PowerPoint slide. So for this question, I want you to try yourself and submit as the assignment 2 uh, in the author. Okay, so let's begin now. So now region Y less than 0, consists of a perfect conductor. Perfect conductor. So what you can think about for the perfect conductor is the E is 0, right? E is 0, so the D is also 0, because it is a perfect conductor. While the region Y greater than 0 is a dielectric medium with this, dielectric constant. So if that is a surface charge, surface charge, you see this is the rho x on the conductor. Determine the D and also the E at these 2 points. At these 2 points. So first of all, let's draw a bit. Let's draw a bit. So maybe this is your y-axis. Y-axis. So for less than 0, which is this one, it is a conductor. It is a conductor. It's a conductor. While for the region Y greater than 0, is a dielectric mediums. This is the medium, first medium. It is 2. So if there is a surface charge, surface charge of 2 nano. Imagine surface charge, on the conductor, and it is 2 nano coulombs, rho x. Determine the E and D at these two positions. So we roughly locate these two positions in our figure. So the X and also the Z, they are in at this axis. So imagine 3D, you just view from side. View from side. This is Y. So X and Z, they are here. So we are concerned about the locations of this point, right? So for the point A, you look at its Y. The Y is -2, so it is somewhere here, -2. This is point A. For the point B, it is 1. It is 1. I don't really care about the X and also the Z, because I know that they are along these directions, along this plane. So B will be upper, will be located in the upper portions. For the A is located, at the bottom portions. So meaning that you have to find the D and also the E at these two regions. Find these two regions. Let's look at the A first. A is much more simple, right? So you know for the A, the D is equals, this is and then this one is a medium 2, and medium 2, and this one is medium 1. So the D2 is equal to 0, as well as the E2. It is 0. So meaning that the E2 tangential, E2 normal component, they are all 0. They are all 0. So basically, at the position A, this one will be your flux and also the electric field intensity. There is no electric field in this region. There is no electric field. There is no electric field. So what is the relationship? So we know that the E1 tangential, is equals to the E2 tangential. So since the E2 tangential is 0, so the E1 tangential is also 0. How about the normal component? Is it 0? No, it is not 0, because we have the other relationship, right? D1n, minus the D2n equals to the rho x, rho x, surface charge density. Surface charge density. So for our E2, E2 is D2 is 0, so as well as this one is also 0. So your D1n is equals to rho x which is 2 nano, right? 2 nano. Okay, and your E1N will be equals to D1N divided with the epsilon 1, right? Epsilon 1. So this is the formula. Okay, so your D1N is 2 nano, divide this one will be equals to, this one will be equals to epsilon R1, multiply with the permittivity of free space. Permittivity of free space. So question tell us the ER1 is equals to 2. Okay, so times this one epsilon naught, you can get it from a calculator. So now you should calculate your D normal. E normal, 2.9 divide 2. So you get 112.94. And this is 1n. This is 1n. Okay, so they want the E and also the D, okay, and consider the vector quantity as well. Alright, so just now we have get this E1N, E2, E1N, yeah, and E1T. So our E, okay, will be the combinations. So this one will be the combination of X component and also the Z component. So this one, how to should write this? Oh no, Y component. Okay, so this is a normal component, E1N normal component. Okay, normal components. So this means that it is in the directions of Y. In the directions of Y. So you just write down 112.94 in the directions of Y volt per meter. Because why is Y direction? Because it is a normal component. So I explained to you before, normal component is heading in these directions. Okay, with respect to the boundary between two medium, 90 degrees, the angle. So now let's look at the D. Okay, the D, because we need to find out what's the D1 also. Okay, so for this one, okay, it also stands for the D1T is equals to 0. Same things. So D1N is equals to 2 nano. So you just put here 2 nano in the Y directions. So this one is coulomb per meter. Coulomb per meter. Coulomb per meter square. Coulomb per meter square. Alright. So we move on to the next questions. Next questions is this one. Okay. Example 222. This one. Okay. So now we have a plane Z equals to 4. Okay. And this plane is the interface between two dielectric. So you just draw it. Interface between two dielectric, and this is at a position Z equals to 4. Z equals to 4, meaning that here is the Z directions, Z axis, two dielectric. So the dielectric in a region greater than 4 has a dielectric constants, okay, of 5. Okay, And the electric field over here, okay, is equals to 6x minus 12y plus 8z. Okay, so if the dielectric constant is 2 in the regions z less than 4, so find the electric field intensity in these regions. Okay, the angles E1 and E2 met with the interface. Okay, met with the interface. So met with the interface is, for example, this is your E1. Met with the interface will be this one. Okay, met with the interface. Okay, so let's see how we can find it. So first of all, we call out the first boundary conditions, okay, which is this one. Okay, E1t equals to E2t. Okay, so let's look at our E1. Okay, our E1, which is 6x minus 12y plus 8z. So like I explained before, normal component is the component that has a 90 degrees, okay, with the interface between two mediums. Okay, so this is what we call it as a normal component. All right. So for tangential component will be the components, okay, parallel, okay, parallel to the interface that's separating two mediums. So for this case, if I am telling you this one is the z-axis, okay, is the z-axis. Okay, looking at this E1, E1 you have 6x, okay, which is in the x directions, negative 12y, which is in the y directions, and 8z, okay, which is in the z directions. So which one is the normal component? Anyone? Based on my explanations, which one is the normal component? Which one? Can you guess? Which component? Yes?
6x and like minus 12y.
Okay. No, this is not the normal component. But I'm great that you answer me. Huh? I like you to answer me. Okay. This one is the tangential component. Okay. So, like I explained, this is E normal. E normal component is in these directions. Is in Z directions. So, this one will be your E normal component, right? Because it is parallel. It is in this direction, Z directions. Okay, so while for the 6x minus 12y, okay, they are in these directions. This is Z, so this one will be x and y. Okay, will be x and y. So this one will be the tangential component. Will be the tangential component, E1t. Okay, if you found that it is very hard to imagine, okay, please try to recall back last semester how you define this vector quantity. How you define this vector quantity? Six x, it means that from the origin it moved 6 units in the x directions, right? Okay, and negative 12 units in the y directions. Then after that, only you move up 8 unit in the z directions, right? So this is the vector. Okay, so this one will be the final vector, this one E1. Okay, E1. So imagine now this is a 3D drawing, right? I put it into 2D. I put it into 2D. So this is Z. Okay, so because I put it to 2D, okay, I view it from the side. Okay, so this will be the XY plane, right? XY plane. You just imagine you look this thing from side. You won't see the XY very clear because bottom, right? Okay, you see from side. Okay, you see this plane, XY plane. Okay, so normal component is the component that has a angle 90 degrees with the interface. Okay, 90 degrees with the interface. So this one is 90 degrees, right? 90 degrees with the interface. So Z will be the normal components. Okay, while for the 6x minus 12y, okay, you view it this way. So this one, okay, is the planes that has these two components, right? You have this one and you have this one, okay? So this one will be a tangential component because they are here. Again, tangential component, they are here. All right. Okay, this one is very important. You must know how to split them. Otherwise, you cannot continue at all. You cannot continue at all. So we already know what is the tangential, what is the tangential and normal components. So for the tangentials, it will be this one, 6x minus 12y. Okay, so 1t, okay, will be 6x minus 12y. Right? So our E2 tangential will be equals to 6x minus 12y as well. Okay, very simple. Okay, very simple because this is their relationship. Okay, the tangential electric field will not have any changes when it across two mediums. Okay, same. No changes. Okay, so this one will be your E2 tangential. I will proceed to the E2 n component. Now I want to find this one. Because I want, why I need to find this one? Because E2 is equals to E2n, okay, plus the E2t. E2t. So for all the electric components, electric field or electric flux density, you can break it into normal component and also the tangential component. When you find it one by one, you can combine and get the E2. So now I want to find the E2n. So the E2n, you cannot find directly using the equation that has the E2. Okay, so you have to use the other set, which is this one. E1n minus D2n equals to rho x. Okay, this is another set of Maxwell equations. Okay, D1n minus D2n will be equals to rho x. Okay, rho x. Okay, this is the second set that you have to apply. So rho x in this question, it is 0. Okay, so the D1n will be equals to the D2n. Okay, D1n is equals to D2n. Okay, so now I want to find E. I don't want to find D, right? We don't want to find D. I only want to find the E2n. So what can I do? Okay, remember this relationship. Okay, so this is a relationship between the D and also the E. So since you know the E1n, am I right? Question give you the E1. So you know the E1n. Just now we already talked about this. So we will put it here. Okay, where the D1n is equals to epsilon 1, right? And the E1n, right? So this one is from here, epsilon 1. Why? Because it is in medium 1. So you have to consider the dielectric a constant in medium 1. Okay, and it will be equals to the dielectric constant of medium 2, okay, multiply the E2n. So you see, now we already see this E2n. This is something that we want to know. Okay, we want to know. So the E2n, okay, will be equals to the E1n, okay, multiply with the epsilon 1. So epsilon 1 will be epsilon R1. Okay, can you see the difference? There is a R here. R means that this is a dielectric constant. So I repeat again. Okay, this is the permittivity of medium 1, and it is equals to the dielectric constant of medium 1, okay, multiply with the permittivity of free space. Huh? So this one you must be clear. I know this one can be cancelled out, but sometimes you have to take into consideration this one in your calculations, just like our previous questions. Okay, you cannot just insert it 2, 3, and then your answer will be wrong. Okay, so this one I will always put it. Okay, minus with the epsilon R2 and this one. Yes, for this case, it can be cancelled out, so no issue. Okay, so E1N is what? So it is at Z, right? From here, at Z. Okay, R1, so R1 is what? R1 is 5, and this is 2. Okay, this is 5, and this is 2. So this one will be the E2N. Okay, E2N. Okay, E2N. So now you got E2T, E2N. Are going to combine them to become E2. So it is 6x minus 12y and plus 20z volt per meter. Okay, so this is how you find the E2. Okay, so when you see this E1, okay, propagate in between these two different dielectric, there is some changes on the electric field. Okay, the XY component same, but the Z component change a bit. Okay, change a bit because there's a difference. Okay, in terms of the dielectric constant of these two medium. Okay, these two mediums. Okay. So I hope you understand the process how to find, okay, the electric field in the other medium when I give you the electric field of the first mediums. Okay? Who are not clear about the calculations, everything, please ask questions. Okay, so now we already settled this one. Okay, the electric field intensity in that region. Okay, that is the region 2. Now we are going to find the angle E1 and E2 met with the interface. So I will draw again the interface. So your E1 is this directions. E1. This one should be theta 1. E1. Okay, so you have a E2. E2. Alright, so met with the interface will be this one, theta 1, and this is theta 2. Now you need to find this thing out. Okay, you need to find this thing, okay, by using the trigonometry method. Oops, maybe I shouldn't draw here. Alright, and here you have your ET component, E1 T component, and here you have your E2 T component, right? E2 T. Okay, it's a triangle. You can just use the trigonometry method. Okay, so if you're using the magnitude, okay, of E1 and also this E1T, you'll be using the cos theta 1. Okay, it will be equals to the magnitude of E1T divide with the magnitude of E1. Magnitude is a length. It's the length. Okay, to be easier, is a length. Okay, so how to find this E1T? Okay, so E1T is equal to 6x minus 12y, right? So its magnitude will be this one square and this one square, right? Okay, so you can calculate yourself. So how about the magnitude of E1? What is E1? It has been given by the questions. How to calculate the magnitude? Yes. So you can find the theta 1. Okay, you can find the theta 1. Square root 180 divide square root 244. Okay, and shift cos, you get 30.81. So this is the angle over here met with the interface. If you get other answer, just let me know in case I'm the one who calculate it wrong. Alright, if there is no, then we'll proceed to the E cos theta 2. Okay, so this is the angle that the electric field in median 2, okay, met with the interface. Okay, so you will use the E2T, E2. Alright, tell me again what is the value for this E2T. For the E2, 580. 580. So let's calculate what is the theta 2. So this one is my theta 2. So I hope you get the same. Right. So this one is the angle. Okay. So we have complete these questions. Is it answer given? Okay, answer not given. Let's try this question 2. So a homogeneous dielectric, okay, homogeneous I explained before. Okay, it means that for that dielectric, okay, at all point, okay, of this dielectric, they have a dielectric constant of 2.5. Means that it is uniform lah, uniform. Uniform. The whole structure has a dielectric constant of 2.5, filling the regions x less than 0. So you see this one is slight difference because now it is x over here. Okay, x over here. So this one is will be the YZ plane. Okay, YZ plane. Okay, so epsilon R1 equals to 2.5. While the region 2, okay, it is a free space. Okay, so for free space, okay, it is epsilon naught, okay, or is epsilon R1 is equals to 1. This is for free space. That's why when we always mention the free space, we just put this one because its dielectric constant is 1. Okay, so if the D1 is this, okay, nano coulomb per meter square, find the D2 and also the theta 2. This one is they're not specific lah. Okay, but this one I want you to find this theta 2, okay, map with the interface. Okay, map with the interface. Alright, okay. So what we should start? Okay, what we should start? We should start analyze this one. Okay, because we are going to break it into tangential component and normal component. Okay, so this one is over. So test yourself. Which one is the D1T? Is the tangential component, and which one is the normal component? Can anyone tell me what is the D1T? Anyone?
Y and Z.
Yes, very good. Y and Z. Okay. So tangential component will be a component in these directions. So Y and Z here. Yeah, very good, very good. Okay. So automatically, this 12x will be the normal component. Eh? Okay. So after we identified this one, okay, we use our first boundary conditions relationship, okay, which is this one. Okay, which is this one. And we know that this is equals to this, right? Okay, so we are going to convert it into the D, okay, because we want to find the D2. We want to find the D2. Okay, so D1T, E1T will be equals to the D1T, okay, divide with the epsilon 1. Divide the epsilon 1. And the D2T will equals to D2T divide with the epsilon 2. Okay, so this one is from here. All right. Okay, clear? So D2T is what we want to find. Okay, it is equals to epsilon 2 D1T, right? Divide with epsilon 1. Epsilon 1. So we have to, sorry, this one is just now it says that this one should be 2. This is medium 2, okay, and this is medium 1. Medium 1, medium 2. Okay, so for the epsilon 2, let's see. Okay, this is the free space. It's a free space. So free space has a dielectric constant of 1. Okay, I told you before. Okay, and epsilon naught. D1T, D1T is this one. Negative 10y plus 4z. Negative 10y, okay, plus 4z. Sorry, plus 4z. Divide, okay, epsilon 1, so R1, and epsilon naught, so this one you can cancel it, make it 1. So R1 is equals to 2.5. 2.5. Okay, so negative 10 y plus 4z divide with 2.5. Okay, so you can calculate. So this is negative 4 1.6. Okay, so this is coulomb per meter square. Coulomb per meter square. Oh, right. Sorry, just now I neglect about this one. Nano. So everything is in nano. Everything is nano. So this one also nano. Nano. So this is a D2T. D2T. Okay, now we look at the second set, okay, of boundary conditions, which says that d1n minus the d2n equals to the rho x, equals to rho x. So now we wish to find the d2n, right? The d2n. Okay, so this is 0. So the d1n is equals to the d2n. Okay, so the d2n, okay, this one will be very direct. Let's just take the value over here, 12x. 12x. And this is nanocoulomb per meter square. Okay, so now we combine them. Okay, d2n plus d2t. So it will be 12x, okay, minus 4y plus 1.6 z, right? Nanocoulomb per meter. Okay, so this one will be a d2. Okay, d2. Okay, so any questions so far?
Now it's okay.
Okay, clear. All right, so we look for the theta 2. Okay, theta 2. So now you will have a flux that is positive. X, x is also positive, right? Okay, so this is our d2. So we want to find the angles met with the interface, this angle. Okay, so we'll be using the, maybe I will just draw again, d2. Okay, so this is the interface. Okay, theta 2. Okay, so your E2 tangentials, D2 tangentials is this one. Okay, so you can use the cos to find again. All right, so now adjacent, okay, magnitude of the D2 tangential, okay, divide with the magnitude of D2. Okay, so 2 tangentials. So this one will be 4 square plus 1.6 square. So 18.56. Alright, so the D2 will be 144 plus 16 plus 1.6 square. Okay, it will be square root 162.56. Or if you want to straight away apply the square root, it's also fine. It's up to you. Okay? Are you getting this answer?
Yeah.
Alright, huh? Okay, so we complete this one. Okay, let's look at this example 23. Okay, very similar questions. You will find that the questions they are very similar. You will have two mediums. Okay, so now given that okay, you have your E2. Okay, you see E2. So E2 is over here. Is equals to 10x plus 6y plus 12 z. So find the E1. Okay, E1, and the angle E1 and E2 max with the y-axis. Okay, max with the y-axis. So it means that if this is your E2, okay, E2 met with the y-axis. This is the y-axis. So please find the angles here. Oh, sorry, this is 2. And this is your E1. Okay, met with the y-axis. Okay, it will be this angle. Okay, met with the y-axis. This angle, E1. Okay, so I want you to try now and ask me questions and submit this one to the individual activities, okay, in our outer classroom.